Welcome to The Explainer. Today, we're diving into the ultimate architectural blueprint. But instead of skyscrapers or bridges, we're looking at the fundamental building blocks of matter itself. We are going to explore the intricate, invisible architecture of the atom. We're talking about the electrons, protons, and neutrons that literally build our reality.
It's a massive question, isn't it? I mean, when you look up at the stars, take a deep breath of air, or even just look down at your own hands, what is the universe actually made of? To answer that, we have to endure a pretty drastic shift in scale. We have to zoom way in, moving from the vast, macro reality of galaxies right down into the microscopic core of a single atom. Because absolutely everything around us is ultimately powered by the delicate balance at this incomprehensibly tiny scale.
Here is our blueprint for today. We'll introduce the building blocks, then individually meet the electron, the proton, and the neutron, uncover the rules that bind them together, and finally, scale back out to see how they impact the real world.
Okay, part one, introduction, the building blocks. Everything around us, all of chemistry, all of physics, is dictated by a microscopic trio living inside every single atom. And it's actually fascinating how rapidly humanity uncovered this invisible world. In 1897, J.J. Thomson discovers the electron. Not too long after that, Ernest Rutherford uncovers the proton. And boom, by 1932, James Chadwick completes the trio by discovering the neutron. In just a span of a few decades, humanity completely unlocked the blueprint of the atom.
Moving right along to part two, meet the electron, the negative energy carrier. So let's meet our first character. The electron is this hyperactive particle that lives life on the edge. By definition, it's a negatively charged subatomic particle. And a quick cheat code for you, just remember electric equals negative. But it doesn't just sit still, right? It revolves around the nucleus in specific energy levels, or orbitals. It defines the very boundaries of the atom, operating in this state of constant, erratic motion rather than following some predictable planetary path.
Now check out this mass. 9.11 times 10 to the negative 31st kilograms. That is impossibly small. It's almost non-existent. But this near weightlessness is absolutely crucial. It's exactly what allows the electron to behave the way it does, zipping around the atom's outer limits at incredibly high speeds.
Because of that extreme speed and its peripheral position, the electron has a huge job in our atomic architecture. It's basically the social butterfly of the atom. It dictates all chemical bonding, it determines exactly how reactive an element is going to be. It's the particle that reaches out, interacts, and binds the physical universe together by constantly trading and sharing spaces with neighboring atoms.
Which brings us to part three, protons, the element's identity, or the positive core.
If the electron is the atom's social butterfly, the proton is the uncompromising anchor locked safely away in the nucleus. A proton is a positively charged subatomic particle. So, second cheat code, proton equals positive. It sits right at the absolute center of the atom, establishing a fundamental steady anchor point for all that chaotic electron energy buzzing around outside.
And look at the mass here, 1.67 times 10 to the negative 27th kilograms. Okay, yes, it's still incredibly tiny to us, but in the atomic world, the proton is massively heavier than the electron. This heavy mass creates a fascinating landscape. You have this really dense, unmoving core surrounded by lightweight, buzzing energy.
So the crucial point here is that protons are the ultimate ID tag. The atomic number, represented by the letter Z, is literally just a head count of your protons. It absolutely defines the identity of an element. If you change the number of protons, you physically change the element itself. Furthermore, these protons remain completely untouched during normal chemical reactions. They stay locked in the vault. And, fun fact, in a completely neutral atom, there's a perfect balance. Your number of positive protons will always precisely match your number of negative electrons.
Let's move to part four, neutrons, the mass stabilizer, the silent partner.
Sharing that center stage with the proton is our third character, the neutron. Your final cheat code, neutron equals neutral. It is a subatomic particle with an absolute zero electrical charge, but it has immense structural importance right alongside the protons in the dense nucleus. Even though it lacks a charge, the neutron acts as the architectural glue. Think about it. You're packing positively charged protons tightly together in the nucleus, and naturally they want to repel each other. They want to push apart. Neutrons step in to balance out that intense tension. Their mass is almost identical to a proton's, and without an appropriate neutron-to-proton ratio, the nucleus would simply fall into dangerous radioactive instability. They also play a critical role in the formation of isotopes, which is a big deal.
Part 5. The rules of atoms. Correlation between particles.
Now that we really know our three characters, let's look at the mathematical rules that govern them. And honestly, it's pretty straightforward. The atomic number, Z, is just your strict head count of positive protons. That's the baseline. If Z is 6, you have 6 protons, which means you are always dealing with carbon, regardless of what the other particles are doing.
Then we have the mass number, which is represented by the letter A. The mass number is simply the combined weight of the nucleus. So the sum of our heavyweights, protons plus neutrons. Since the electrons contribute virtually 0 weight to the whole shebang, just adding the protons and neutrons together gives you your total atomic mass.
And this beautifully explains how ions are formed. Because the protons are locked securely in the vault of the nucleus, an atom alters its overall electrical charge solely by trading its electrons. If an atom loses negative electrons, it becomes unbalanced in favor of its positive protons, creating a positive ion known as a cation. On the flip side, gaining extra negative electrons tips the scales the other way, creating a negative ion called an anion.
This mathematical balance also explains isotopes perfectly. Take carbon-12 and carbon-14. They share the exact same identity because they both have exactly 6 protons, but they carry completely different weights due to a varying neutron count. Carbon-12 has 6 neutrons, while carbon-14 has 8. It's the exact same element, just with a different mass stabilizer count. Finally, Part 6. Atoms in the real world. Zooming out.
So why does understanding this tiny, invisible architecture actually matter to us in the macro world? When we synthesize the roles of all three particles, the fast bonding electron in the orbitals, the heavy identifying proton in the nucleus, and the stabilizing neutron right alongside it, we basically get the foundational matrix for all advanced science. This synthesis explains exactly how matter interacts, transforms, and holds together. I mean, these microscopic properties are literally what power our modern lives. The flow of electricity operating our cities, and the device you're using right now, that is just the manipulation and movement of those lightweight electrons. The massive power generated in nuclear energy stems entirely from tweaking the tight bonds between protons and neutrons inside that dense core. And modern medicine relies heavily on specific isotopes to run advanced, life-saving diagnostic scans.
We've gone from the vast macro universe down to a mass of 10 to the negative 31st power. And it leaves us with a pretty profound question. How does something so impossibly small hold the entire universe together? By finally understanding the delicate interplay of just 3 characters, the electron, the proton, and the neutron, we unlock the fundamental forces that build our reality. Thanks for joining this explainer. Keep exploring, and I'll see you next time.